The sol gel method is the method we generally apply for bottom-up synthesis of nanomaterials. And as the name suggests, that it involves actually solution as well as gel formation. So whenever we dissolve a particular substance in a particular solvent, if it goes to the solution phase, then immediately we get a sol or a solution. And when you somehow allow the solvent to evaporate, then ultimately the solute particles which make up that particular solution, they come towards one another, and ultimately you will be having a gel. So what is this particular sol gel method? This is one of the primary method utilized in the bottom-up synthesis. Now bottom-up synthesis, as the name suggests, it is the building up method of producing nanomaterial, and where we take actually the basic units and we allow the basic units to combine with one another, so that ultimately at some level we can stop that reaction, and at that level we will be able to get the nanomaterial. That means material where the dimension, any one of the XYZ dimension is in the nano range, that is within 1 to 100 nanometer. So this particular sol gel method is called a wet chemical technique. Why wet? Because you are utilizing one solvent. So this is the most widely used actually method. The scientists are actually fond of this particular method, and here mostly this particular method is utilized to create metal oxide based nanomaterial. Metal oxide based nanomaterial, just like titanium dioxide or zinc oxide or copper oxide. Now, as I said earlier, that oxygen when takes up 2 electrons will lead to the formation of O2 negative, and these oxide ions, when they will be close packed, will give rise to some interstitial spaces, and in that interstitial spaces, if you can allow any metal ion to go and fill up that particular state, and then somehow that kind of oxide, metal oxide, will be formed, and if the dimension you can keep in the nano range, immediately you will get the metal oxide nanomaterial. So there is so much utility of metal oxide. For example, if you say titanium dioxide, this is a widely used photocatalyst. Photocatalyst means a catalyst which works with the help of light. Now the thing is that suppose you have produced one solution of a particular solute and you want to have a nanomaterial out of that, then the solutions, if 2 or more substances are taken into the solution phase, and then you are allowing the solution to mix with one another uniformly, and then you allow it to condense to go for the gel formation, and so that you ultimately convert them into a network structure, and they will allow themselves to condense in such a way that ultimately you will be having a definite nanostructure. But sometimes it is found that even if you mix a solution A with another solution B, they may not combine with one another even if you allow them to go for the gel formation. That means they need some binding force, and that binding force actually acts like a glue. That binding force actually acts like a glue which will bind the 2 substances you want to combine or you want to assemble. So in the synthesis of actually nanoparticle with this particular method, that means the sol gel method, actually it involves sometimes utilization of some other reagent also along with the parent materials of which you want to prepare the nanomaterial. Suppose you have titanium dioxide, you want to prepare titanium dioxide, then along with a precursor or a reagent based on titanium, you may have to use some other material which can act as a glue. So this sol gel procedure actually takes place in a number of steps. So in the very first step, you have to have hydrolysis of the metal oxide. That means you must have the solution of the metal precursor. If you want to prepare a metal oxide based nanomaterial, then you must have the starting reagent, and you need one solvent so that you can go to the solution phase. So you can use water if that particular thing is soluble in water, and if it is not soluble in water, you have to take another solvent, and that may be an alcohol or any other solvent where your parent compound dissolves. So if it dissolves, then ultimately you will get a solution which we call a sol. So after the formation of the sol, in the next phase, what you do, you allow different type of salts to mix, or you allow the solution which contains different type of materials, A, B, C, etc., of which you want to combine to get ABC material or ABC nanomaterial. In the next step, what we do, we allow the solvent material to evaporate or to go out from that solution phase, and immediately when the solvent starts leaving, this will go for condensation phase. So when you decrease the amount of solvent in the material, it will go on condensing gradually, and ultimately that when the solvent will leave, then immediately a porous structure will be formed. There will be the ABC parent material, what you took, they will come closer to one another, and this condensation, or you can say it polycondensation, and that will lead to formation of some kind of bond between A, B and C. If you are taking metal atom, and if you are utilizing a solvent based on water, maybe water or maybe hydroxide, then there is every possibility that the metal hydroxide metal bond will be formed, or metal oxygen metal bond will be formed. So if you want to have metal based nanomaterial, then when the solution containing the metal precursor or the metal parent compound, when it is allowed to condense, then it is every possibility that it will result in the formation of metal hydroxo or metal oxo solution. Then the polycondensation will take some time. Gradually, very gradually, you allow the solvent to go out from the solution phase, and then you keep it for some time. Slow evaporation of the solvent will result in the formation of porous structure, and then when you continuously allow the solvent to go out of this, and at some moment if you think that I have to cool it immediately, otherwise, or I have to send out the solvent immediately, then you can go for heating. And that heating actually in absence of oxygen or in presence of oxygen, both way you can do. So calcination and roasting. So generally here calcination is done, that means heating in absence of oxygen or air. So when calcination is done, that means heating to a very high temperature immediately to evaporate the solvent present, then you will be getting a structure which is a which will be in the nano range. And how it will be formed? You had one metal substance, metal salt, metal sulfate, metal chloride, anything. You take it to the solution phase by utilizing a suitable solvent, and then you allowing it to evaporate the solvent, and ultimately that will give rise to, if you allow them to evaporate, then ultimately it will give rise to condensation. And in the condensation, previously if you had metal sulfate, metal chloride, metal nitrate, any metal precursor, but ultimately you will be having metal oxide bonds, metal oxide metal, MOM or MOHM, or you can say that we will be having metal hydroxo or metal oxopolymer, and that will be formed in the when we go for the sol-gel procedure, then immediately first thing we want to have is the hydrolysis. Hydrolysis of the compound, of the parent compound you are taking. So you must have the solution of the precursor. What is called precursor? The initial material you are taking, to which you want to have the convert to the nano range. So you take, if you say chromium sulfate, then this will be chromium sulfate solution. If it is iron, this will be iron sulfate solution. If it's a titanium compound, then it will be the titanium compound. Now you see, all the time it is not so that water will be the solvent. You'll be having different type of solvent material. Even the same metal with different anion will dissolve in different type of solvent. So what is the first step for sol gel synthesis is that you first have the solution, then go for hydrolysis. You will be having the sol, or you can say the solution phase, where you will be having the particular metal precursor and a particular solvent. Now if you allow it to condense the cell particle, condense the sol particle means you allow the solvent particle to evaporate, then the xylation will take place and you will be having the gel form. Okay, gel form means the thicker or the more dense material where lesser amount of solvent is present. Now the particles, if you say if these are metal particles, once you remove the solvent, they will come closer to one another, and that may give rise to some bonding between them, and you will be having a new compound. A new compound or a dense material which we call gel. Then immediately once you see that this is called nucleation also, you are allowing a different type of nucleus to combine with one another. Again you allow evaporation of the solvent, you will be getting the aerogel. Still some amount of solvent is there. Heat treatment will ultimately give you the dense, nanomaterial, and this is here is the powder formed from a colloidal salt solution. This is from the Elsevier paper actually. So you will be having the dense ceramic particle, but here also you can go for two different things. This is direct condensation, but if you go for spin coating and dip coating, that means you take another material and you just dip it in there. So if you have a particular substrate and you allow the solution to go through it and then you spin it, that means you allow it to rotate. And when it will rotate, the substrate it is coated with this sol. You just allow the solution to fall here and then rotate it. This will also give rise to a kind of, see, there will be some holes through which they will go out, and it's just like a sieve. It will allow other particles to go, and a minimal amount will be there. Rotate it and you will get the aerogel. Heat treatment, you will get a dense film. That means this is a film where you deposit your sol and then move it in such a way so that a uniform film is created, and then allow the film to heat and you will get the dense film of nanomaterial. And this is deep coating. Instead of allowing to fall on a film, you are taking a particular material or particular form, you dip it, and when you dip it, both sides will be covered by the nanomaterial, and heat treatment will give you a film with nano coating on both the sides. So in the next phase, if you say this is the difference between the sol and the gel. In the sol, the particles are farther apart from more apart from one another, but if you allow the solvent to evaporate, you will be having the gel phase where the nucleation will take place. So bottom up method, if I go for the thing, if the two materials A and B, if we want to allow them to combine with one another, if somehow they don't show attraction for one another, then you have to use some foreign material. This particular slide will show you that if that sol gel processing leads to hydrolysis and condensation, but they don't show any attraction for one another, then you have to add alkoxide based precursors such as silicon tetraethyl orthosilicate, and this particular material acts as a glue. So in the sol gel process, mostly instead of taking simple metal salts, we take metal alkoxide based precursors. So metal alkoxide, this is actually metal alkoxide means you can go for methoxy, ethoxy, propoxy, whatever alkoxide you want to have, but normally used is orthosilicates. So you take this, allow it to react with water to get the hydrolysis part done, and you will be having the condensation to give you the MOM bonding. And this is the way you can solve it. You have the precursor, you dissolve it to get the sol, you dehydrate it to get the gel. Rapid drying will give you the aerogel. Surfactant, if you allow another molecule. So we can say that in the sol gel process, we can proceed with the following procedures. First of all, formation of different stable solution of the alkoxide or the solvated metal precursor of which we want to prepare the nano material. Then followed by, after formation of the solvated metal precursor solution, we go for xylation resulting from the formation of an oxide or alcohol-based network. That means the gel formation that will be done by the polycondensation reaction that results in a dramatic increase in the viscosity of the solution, because as the solvent goes on evaporating, or as the solvent leaves the solution phase, the metal precursors or the metal solvated metal metal atoms or ions present there will come closer to one another, and that will lead to the formation of an oxo-breezed metal-metal bonds. And when the solvent will decrease, the medium will get denser and denser, and that will ultimately result in the increase in the viscosity of the medium. And then we allow the gel which is formed in the second step to stay for a while, or that is called the aging of the gel, also called the syneresis, during which the polycondensation reaction actually continues until the gel transforms to a solid mass with the evaporation of all the solvent present here. And this is accompanied by contraction of the gel network and expulsion of the solvent from gel pore. And then ostual ripening, also referred to as coarsening, is the phenomenon by which the smaller particles are actually consumed by larger particles during the growth process. And this ultimately will lead to the phase transformation, which will occur side by side with the aging process. And now the aging process of gel can exceed 7 days and is critical to the prevention of cracks in gels that have been cast. So we can again say that first the solution formation, then gel formation, then aging for polycondensation, and that polycondensation will give us the desired network of metal oxygen metal bond with the smaller particles fitting into the pores produced by the larger ones. Lastly, there will be drying of the gel when water and other volatile liquids are removed from the gel network. And this process is complicated because of the fundamental changes in the network structure of the gel. And this particular process, that means evaporation of the volatile liquids or water present in it, will be not a single state process. Rather, it will involve a number of process with definite constant rate. It will have to look into the critical point value, then falling rate period, second falling rate period, etc. That means the solvent will be, there should be some gradual evaporation of the solvent so that the uniformity of the gel is not lost. The properties of the gel are not only a quick evaporation or a sudden change into the atmosphere may lead to the deformation of the gel form, and ultimately that will deform the nanomaterial from which we will be expecting. Then if we want to remove the volatile liquid by thermal evaporation, then by after evaporation, the resulting gel we will be getting is known as aerogel. And if we have water as a solvent, then the supercritical at the supercritical or at the critical condition, the gel we will be having is called the aerogel. So in case of other solvent, we will be calling it gerogel due to thermal evaporation if the solvent releases the gel surface, and it will be aerogel if we are utilizing some aqueous solution with water as a solvent. Lastly, there will be dehydration because in the surface also there will be bound MOH groups or bound hydroxide groups. So they will be stabilized by they will stabilize the gel against rehydration. And for the dehydration process, we can increase the temperature up to 800 degrees centigrade, and that process we will be calling it calcination. So densification as well as decomposition of the gel at a high temperature that may lead to temperature increase more than 800 degrees centigrade. Then the pores of the gel network will be collapsed and remaining organic species will be volatilized. These are the different steps which we normally encounter in the sol gel process. So this particular process, that is the sol gel process, is widely utilized and is very dear to the scientists because of the possibility of synthesizing non-metallic inorganic materials. Mostly these include glass, ceramic or ceramic material, and that can be done at a very low temperature compared to the high temperature process required for melting glass or firing ceramics. And now the major difficulties to overcome in developing a successful bottom-up approach is controlling the growth of the particles and then stopping the newly formed particle from agglomerating. That means we want to go for the solution phase, then we will allow the solvent to evaporate, and then evaporation will condense the material, giving us the desired network. But if we go on condensing the material, there may be some point that they will simply assemble all together and they will go for agglomeration. And agglomeration will ultimately result in macroparticles instead of giving us nano or microparticles. And there are some other technical issues also in creating nanomaterial by bottom-up synthesis. And these also sometimes gives us unwanted results compared to the ones we were expecting. And that is one such is that, some reactant may left over on the product. Instead of completely removing from the solvent, we may not be able to detach the unwanted material, or we cannot remove the unwanted material from the nanomaterial formed. In that case, the properties of these particular things will be different. We cannot get this particular thing. But the main advantage is the one can get mono-sized nanoparticle by any bottom-up rep. So what is mono-sized? That means first of all, since we will be having the uniform solution, there will be uniform distribution and uniform mixing, and that ultimately will give us nanoparticle which will be similar in size. So this particular method actually is very important in the nanomaterial synthesis. So simply we can sum up that we sum it up in this formation, in this particular way, that in the formation of nanomaterial by bottom-up synthesis, and that also by sol gel procedure, our main motto will be creation of a sol, and that sol, to prepare the sol for metal oxide, normally we go for metal alkoxide. That metal alkoxide, with the help of a particular suitable solvent, will give us solvated metal precursor, and that solvated metal precursor will next be converted to a gel, and that will lead to the formation of actually oxide or alcohol breezed network, which we call the gel. And from that gel, by polycondensation through aging, we will be having the desired nanomaterial, and the aging process can exceed up to 7 days. and we have to be very careful that within this aging process, that means we will have to keep it as it is. We have to be very careful that no loss of properties are observed in the gel. For example, there is no cracks in the gel, and once the gel is dried, that means when all the solvent, whether it is water or it is a volatile liquid, are removed from the gel, then they will lead to the formation of the final nanomaterial. Removal of the solvent other than water will give us the Aerogel, and removal of water from the aqueous solution of a metal alkoxide compound will give us Aerogel. And still, if there is some solvent molecule present, then we can go for calcination, and then through calcination we can get rid of the unwanted material, unwanted hydroxide groups or any other material present there, and after removal of this we will be having the desired nanomaterial. So this is the sol gel process. Again, I say this is the most widely used process and most loved technique for synthesizing nanomaterials. Thank you.